My name is Todd Smith, and thank you, Dr. Peltzberger, for joining us. Today my presentation will be an expert system. Specifically, I'll be presenting a desktop computer repair expert system. When faced with picking a domain, Dr. Y allowed us wide berth. Many ideas seemed interesting, but I settled on what I felt I had the most expert knowledge in. While I would shy away from calling myself an expert computer technician, I do have considerable experience working with desktop hardware. Additionally, I'm a senior here at GSW pursuing a BS in computer science, and I already have an Associate of Science from Dartmouth. So, while other potential domains piqued my interest, I felt it most prudent to choose desktop computer repair. There's my little guy. My presentation today will largely follow the format of our assignment. We have already covered my domain, so first I'm going to introduce CLIPS, then we will take a look at some rules and facts from my expert system in hopes of demonstrating just how easy but powerful a tool CLIPS is. Finally, to close, we will walk through at least 3 run traces of the project code. CLIPS is awesome. For my project, I used a Windows-based version which included many menu-driven conveniences. Included with the Windows installation of CLIPS was a DOS command prompt version of CLIPS, excellent documentation, and several example programs. My project is derived from one of the example programs, AutoCLP. While you can simply input facts and rules or even functions from the CLIPS prompt, it's far easier to do your programming in a simple plain text document than simply load the .clp file into CLIPS. As a rule-based expert system, the desktop repair expert system is comprised almost entirely of rules. In fact, with the exception of 2 functions defined at the beginning of the code, the entire project is a compilation of just rules. As for the 2 functions, ask question and yes or no p, they are simply employed to assist the user in inputting facts. An example of each type rule used and their dependence on the 2 affirmation functions follows. The first 2 rules given in the code are normal computer boot conclusions and no boot just post conclusions. I could have, and a complete solution would have employed a 3rd and possibly a 4th rule here, but given the scope and expected size of this project, 2 were adequate for my purpose. Both of these rules make global assumptions by asserting facts after the execution of the first rule to fire determine computer state, which determines the fact working state computer. Let's look at the first rule and things should become clear. First, we will cover the basics of rules in CLIPS. Notice how the entire rule is inside parentheses. This is required. Also note the keyword def rule, which must always be used, after which the name of the rule is declared, with optional commands following enclosed in quotes. Next we have the keyword declare. Here we are declaring the salience for the rule, and while necessary here for reasons I'll explain in a moment, it is optional, and if excluded will default to 0. Now let us consider the structure of the rule. Basically everything before the implication sign, which is the equal and the greater than, is the if portion, and that which follows the implication is the then portion of the if-then rule format we are all familiar with. It is worth noting from the then portion of our rule the usage of the assert keyword, which is used to assert facts. Now let us consider the first query rule, which is actually the first rule to fire in the system, and explain CLIPS's employment of salience. Here we will also see the employment of the 2 functions included in this project. Notice the basic if-then structure of the rule remains unchanged. You might also note there is no salience value declared. In spoken English, the rule says, if the fact determined computer state is unknown, and the fact repair is unknown, then ask the question, does the computer post? If true, then ask the question, does the computer boot normally? If the answer is false, then set the working state computer does not post. If the computer posts and boots normally, assert, state the fact, working computer normal. Or if the computer posts and does not boot normally, assert working state computer will post. Referring back to the if portion of this rule, notice the conditions for the rule firing. Conveniently, CLIPS allows a fact is unknown to be used as a condition for a rule. So despite this rule having a lower salience value and being located higher up in the structure of the program, because we don't already know working state computer, or repair for that matter, the if conditions are met for this rule. In fact, this is the first rule where the conditions are met by design. As shown in the graph of the system, this rule is the first branch. Once this rule is fired, the then portion of the rule asserts working state computer fact. Next, because the state rules have a greater salience value than any other eligible rule, these rules are checked again first. And if the conditions are met, certain facts can be asserted and the path to a solution is shortened. Finally, let us consider a housekeeping rule included in the project. I stated incorrectly earlier that determine computer state was the first rule to fire. Actually, this is a bit of a misstatement. In fact, the rule above is the first to fire. Notice the only condition is the salience value of 10. Of course, this rule only prints out and formats text. Here's a graph of the desktop expert system, and here's where we were talking about the first rule, and it basically breaks it into 3 different paths that you could fall through. And then here are just, because the other one, when you put all the graph together in one whole graph, it's hard to see. So here's the top level. That was actually the beginning of my trace run. Here's one of the 3 trace runs. So we notice here, on this part, you'll see where we're at in the graph. In this part, it's the rule that we're actually using. Here is where it's actually running in the Eclipse software, and we'll actually run one for the third. Here's the facts that we know at this point, and here we're at the initial. Every run is going to have F0 as your initial fact, and I guess we all know that from the documentation. And here's the agenda. As we sit right now, check power is next. Now this may or may not change depending on how we answer the questions. This agenda will change. And also notice the salience values. With -10, the lowest number being at the bottom of the list, and these with the same salience value, they actually fall in the order where they would fall in the code. So, like I said, here we are at rule determine computer state. Here's just a comment. I just put how's it going to be, just to put a comment. Here's where we're if portion of the rule. So if we don't know the working state of the computer, which is what we're doing here, checking computer state, and once we have an answer, that, like I said, will drop us down, and we'll see that on the next slide. And we don't know the repair, then do these things, which is what we're doing at this step. We came along, we already asked if the computer booted, that got us to the next. Does the computer boot normally? We answered yes. Once we did that, on the overall graph, if you remember, we had 3 different paths we could take, and I color coordinated them. So this is normal boot and normal post. So what happens is we can automatically assert all these things. When I was speaking earlier with the slides, I talked about shortening the path. And this is in fact where we shorten the path, because as you guys all know from experience now, we have those rules sitting in order. And what happens is these rules now, when we get to the not part, which is not on this one, I guess we can look at the next one. When we get to the not part, it'll actually already be answered. So the if part of that rule is not true, so it keeps going on. Here we see where the first run terminates. So we come down. Can we get text from the keyboard? Yes, we get text from the keyboard. And here's the question, and then we move down the graph. And like I said, it drops us down the next thing. And on the next question, can we get the mouse to move on the screen? We couldn't get the mouse to move, so it terminates by giving us an asserting repair. And once repair is asserted, if you notice in all our queries, there's repair. So once we know repair, the run terminates. And here's just another run. We start out, of course we're goal driven. We're looking for the goal repair. We're trying to assert the fact repair. So we start again. Does the computer post? This time we put no. It asks us the next question then. Is the computer plugged in? It's the same thing. We're just simply moving through the graph. And notice as we answer these questions, notice our facts are asserted. And here we're just proceeding through. The next question, the power supply was good, so we moved on to the monitor. Another thing I wanted to point out, when we talked about the first two functions in the beginning, notice I have caps for the no. Notice the middle is a mixture of upper and lowercase characters, and that was what the first function did. It basically took your value, and if you put a y in, it bonds it to true. If you put yes in caps, it bonds it to true. It doesn't matter if it's capital or lowercase. It just makes inputting the text a little easier. Again, we're building facts, we're answering questions, and we're looking at our agenda. Another thing that's interesting to point out, if you notice the asterisk and the comma, what those indicate is how many parts do we have for our if. So if you have two asterisks, there's two conditions that have to be met for your if. If you had three, there's three. And then of course we see here where the does not boot terminates. Your computer is fine. If it proceeds all the way through and it gets to the last rule, which is no repair, which is salence of -10, which means this is the very last rule that'll fire because I made that the lowest salence number. If it gets all the way through there, it assumes we've checked everything, there's no problem, and you're likely the problem. So I'm going to stop this real quick and we're going to run through an actual one with clips real fast. If you guys bear with me 2 seconds. Windows. Okay. Now, we're going to load. And computer 6. If you notice here too, I guess, and you guys all experienced the same thing. I basically started out with my first one, and it basically took 6 versions. I thought I had it good, and then the graph that Dr. Ulemanov required, as I was doing it, I found several mistakes. So as you find mistakes, of course, you make changes. And for me, it wound up being, I got to computer 6. So you load it. The first thing you have to do after that is you have to, well, it's easier just to do it here. You just have to reset every time before you run, and then you simply learn to type, and then you run. Alright, so Ted, does your computer post? Yes. Ted's computer posts. And notice I can just put a y in, and it also takes that as true. And again, that was the work of the functions that were up top. Does your computer boot normally? Ted's computer boots normally. Can you input text from your keyboard? Notice here, and this is part of the expert system, and it would have been better if I could have printed out the graph and you guys could have all had a picture of it. Here, because the computer posted and booted, we can rule out that the hard drive is the problem. We can rule certain things out. We know the power is not the problem. So you notice it's not asking the same questions. We've taken a whole different branch because we can assume certain things are good. Can you put text in from the keyboard, Ted?
No.
Are you sure? I'd like to go a little farther than this. How about typing? Oh, great job, Ted.
I just fixed it.
Can you get the mouse to move? I don't care, it's up to you.
No.
He doesn't get the mouse to move, it terminates. Now, and I'll just sum it up with this. It's not a complete system by any stretch of the imagination. It could be a lot more sophisticated. And again, if you were to look at the graph, you'll see a lot of times I just do a single branch after we've dropped down. I just wanted to demonstrate that we could branch and make rules dependent on other rules, but because of time and intelligence, that's about as deep as it went. Does anybody have any questions?
Oh.